In this video, we're going to go through the aldol condensation reactions. Now, what is an aldol condensation? Now, this is a reaction between two molecules of aldehyde in the presence of a base. So if you reacted this with itself or any other type of an aldehyde in the presence of a base, you're going to have an aldol being formed. So this is the aldehyde group of the aldol, and you are also going to have an alcoholic part of the molecule. So this is what you're going to have. And the question is, why do we have only one R group within the product whilst we had two over here? What is behind that? Now you need to know that this R group might be a CH3 group, that is a methyl group. If you have that, that might well become this part. Then this, which is a carbon atom, will be this carbon, which is here. And you might not really be able to see that except we carry out the mechanism for the reaction. So we're actually going to do that in a little while, but I just need to clear up some things. If you have an aldehyde, which I'm actually going to represent in this form, so this is an aldehyde. Here we have a carbon atom. This is a carbon that you see right there. Now, if we took this R group and represented it in more specific forms, let us say the hydrogen is on this other side, and we got the oxygen atom on this other side. Let us say we chose a CH3 to be our R group for this case. Notice that we have 4 hydrogen atoms within this compound. Now the first 3 hydrogens are connected with this carbon atom. Bear in mind there is another carbon atom within that position. That is going to be called as a functional carbon atom. This one therefore will be called as a functional hydrogen. That is because the hydrogen is connected to the functional carbon. These hydrogens are not directly connected to this carbon. They are actually connected to this one. Now, what is the name of this carbon atom? This carbon atom, for one, is called as a functional carbon. Since we have a carbonyl group here, you could well call this as a carbonyl carbon. Now, what is the name of this carbon? This is actually going to be called as an alpha carbon atom. This is a carbon atom which stands or sits immediately beside or adjacent to the carbonyl carbon. In this case, this is a carbonyl carbon and this is clearly adjacent to it or beside it. That is going to be called as the alpha carbon. Now, everything that the alpha carbon is connected to will be called as the alpha of whatever it is. In this case, we have 3 hydrogen atoms. So that is going to be 3 alpha hydrogen atoms. In order for an aldol condensation to work, you always need to have at least 1 alpha hydrogen atom. If you do not really have that, the reaction will not occur. Now, I might not really say reactions might not occur within that whole compound or mix-up of compounds. Reactions might occur, but that is not going to be an aldol condensation. Maybe some other reaction actually might take place, but not the aldol. For the aldol to work, you necessarily need to have at least 1 alpha hydrogen. Now let us give some examples in more specific terms for this reaction. Let us say you had a CH3, CHO, which this is ethanol or acetaldehyde, and let us say you reacted it with itself in the presence of a base. This is going to give us something like this. So I'm going to have a CH3 here, and we're going to have oxygen. We're going to have this, and we will have the alcoholic group on that part, and we are going to have, okay, so I actually made some mistakes. I needed to make a hydrogen appear here. On this side, we're going to have the CH3. Because we must have the aldehyde group for one and the alcoholic group, and hence the name aldol, whilst you have this as the first part You have this as the second part, which makes up the full name of the aldol. Hopefully you understand that. Now let us see some other examples. What if you had CH3, CH2, CHO, and these were reacted with CH3, CHO, and in the presence of the same base? What is this gonna give? Now here on this part, we actually have 3 carbon atoms, whilst here we have 2 carbon atoms. Now let us make this to serve as the first part. So I will rotate this and bring it to this other side. This is gonna be the aldehyde group, and this carbon atom will stand for this carbon, whilst this carbon is a carbonyl carbon which is in this position. So we need to write out where these are gonna be. So obviously this would produce the alcoholic part of the compound. So I need to connect them, and this must be connected to this carbon atom with an oxygen. And on this part, we're gonna have something like this. And so that is what we're gonna have. This will be the molecule forming. Now the question is, how do you really know how to form the products? How can you find these products? How can you form them? And the answer to that question actually lies behind mechanism. We need to work the mechanisms for these reactions in order to find out why these molecules are forming. Now in my head, I already performed it, so I actually know what should be formed. Now let us work it out on the page, on the board. So I'm just gonna wipe everything out. So let us start with the major one. Let us start with R1 and let us connect this. So I'm just gonna make it be a little bit more explicit. So this is one molecule of the aldehyde. Now, of course, we know that the aldehyde needs to have an alpha hydrogen, and we might not actually be able to show that except we represent a type of the R group. Whoa, I needed to write this. So let me wipe that out and redraw it. So let us say you have this, and this is connected to a CH3. Now this could be written this way. So I'm just gonna write it here. This is a CH2 and this is a hydrogen atom. And this will be reacted in the first case with a hydroxide ion. I might well take this out just to provide space. And the first reaction is the fact that the oxide ion is electronegatively charged. We have a hydrogen here, which is obviously positively charged. So this is actually going to collect this, and this bond between the carbon atom and this other hydrogen, this is actually a bond between this carbon and this hydrogen, not the hydrogens, which are 2 right there. So this is going to return to this carbon, and we're going to form something like this. That is going to be a CH2 with a negative charge. And this negative charge stands for the fact that you actually have a lone pair of electrons on this carbon atom. This is called an inner ion. And there could actually be resonance that occurs within this place this way. If you have this lone pair of electrons, bring the lone pairs and produce another bond between this carbon, that is the alpha carbon, and the carbonyl carbon. That is going to cause one bond from here to detach. That is because carbon atom cannot have more than 4 bonds. So that would really need to leave. So that is going to give something like this because it is resonant and the same. I'm actually going to use multiple arrows in both directions. So this will be an oxygen with a minus, and here we're going to have a double bond with a CH2. Now, what does this mean? If you have an excess electrons or an excess lone pair of electrons on the oxygen, that is going to make the lone pairs to be 3. Initially, there was 2. Now we're going to have a 3. Now, because we know that this form is actually a resonance form, this could well collapse and recreate the double bond between this oxygen and the carbon. And because we know that carbon atoms cannot have more than 4 bonds, this is already 1, 2, 3, and 4. Now, oxygen attempts to create another bond between itself and this carbon. That is going to cause this other bond to remove away from there and reform the lone pair of electrons that was there initially. So this is the meaning of the resonance forms that I was talking about. Now, this one will be more useful for this reaction. So we're going to go back to it. So that is what you have. Now this is just one molecule of the aldehyde. Remember, we were actually required to carry out the reaction with 2 molecules. Now the hydroxide ion which was formed, this is actually detaching a hydrogen atom, which is also called as a deprotonation reaction. This first aldehyde will be deprotonated and that is going to form the enolate ion. Now I need to write that somewhere here. So this is going to be an enolate. So that is going to be an enolate ion. The enolate ion will now react with the second molecule of the aldehyde. So I'm just going to write that here. Okay. So let us make it turn this other way. So this is the second molecule of acetaldehyde. Now this is going to serve as a nucleophile for the fact that it has a negative charge. Now there is a carbon atom here, another carbonyl carbon, because we have the dipole moment being in this way. That is, you have a hoarding of electrons away from this carbon atom by the oxygen atom. Oxygen is more electronegative as compared to the carbon atom. So that is going to hoard electrons away from the carbon and make the carbon atom become positively charged. So in this case, we say that the carbon atom is actually positively charged rather. So in this case, we would have this bond, the lone pair of electrons or the negative charge on the carbon atom connect to this carbonyl. So this is going to be the next arrow, and of course we're going to have one bond away from the oxygen detached. As you well know, we should not have carbon atoms having more than 4 bonds. So that is the reason why this one bond has to get out. So this is going to give us something like this. We're going to have a aldehyde group here, and there is a CH2. Need to rewrite that. And this is connected to this carbon. I'm just going to represent it now. So this carbon is this one, the carbonyl carbon. That is connected to an oxygen, which carries a negative charge. Now this is a hydrogen atom. Well, I might just write it here. Now we have the CH3, which is on the other side of the carbon. I'm going to write it here. Well, so I'm really having some problems writing that. Well, so that is what we're going to have. Now, buried at the back of your mind, we actually had water forming. As you had the hydroxide ion deprotonating this system, that was a removal of hydrogen. So that should form something like this. Now, in this case, you are going to have this oxide ion use a lone pair of electrons, which is an excess, and collect this hydrogen, and that is going to cause this bond to detach and reform the hydroxide ion. Remember, from the start of this video, we actually said the hydroxide ion is serving as a catalyst. You can actually rewind the video and go to that point where I actually say that. So that forms hydrogen. This hydrogen combines with the oxygen to form the hydroxyl group. So you are going to form something like this. This is a hydrogen. and this is connected to carbonyl, and then you got a CH2 right here, and this is gonna be carbon atom. In this case, I'm just gonna write it there because we already know what should be there in it. And with this is gonna be a CH3. You could leave out this hydrogen atom because we do not really need to write it. That is the whole idea behind line structures. You don't need to write every single element or atom which needs to be there. So this will be the product. Now writing it out in line form would obviously look this way. And you have a CH3 right here. So this will be the molecule under constitution. This is going to be the answer to that compound. And just for the sake of more understanding, we're going to try another one. Let us say in this case you had a cyclic aldehyde, something like this. This is not benzaldehyde. This is basically cyclohexyl aldehyde. That is because we have this ring as a cyclohexyl ring, not a benzyl ring. If we had this bonds inside of this should have been a benzaldehyde. In this case, that is not. So this is what we have, and this is cyclohexyl aldehyde. And let us say this were reacted with something like this. Now, what is the name of this aldehyde? For one, we know that this is an aldehyde because we have the aldehyde group connected in that position on the other side. Now, what you need to do, you need to count out the number of carbon atoms which are present within the whole straight chain. So if we started from here, this is going to be 1, and this will be the second, this is going to be the third. So that makes propanol be the name for this compound. If you don't want to call it that way, you could call it as ethylaldehyde. In this case, we said cyclohexyl aldehyde. This whole form is called as the aldehyde. So what is going to be the product of this reaction? So let us work out the mechanism to show, to find out what is going to be the answer to the question. Okay, so I'm actually going to start with this one. So I will take it to this other side, and we're going to have a molecule look this way, and this is what you have. Now, we have this to be the alpha carbon, and because the alpha carbon atom needs to have 4 bonds, as a matter of fact, every carbon atom needs 4 bonds. This carbon actually has its 4. This is 1 bond, this is the second, this is the third, and this is going to be the 4th. So that is full and complete for the carbonyl carbon. Now for the alpha carbon atom, which is the carbon atom which is immediately after the carbonyl carbon, that is this one, and that actually contains 4 bonds. This is 1, this is the second, this is the third, and this is the 4th. Now notice that from the beginning, we didn't actually represent this stuff. You actually need to know that from the top of your head, because this actually is the reason behind the line structures. You do not really need to write the hydrogens, except you need to write a hydrogen atom which is connected to a functional group. That is allowed, but not for the normal, or I would just say normal hydrogen atoms which are connected to the carbon atoms. Those are ordinary hydrogen atoms, so you don't really need to write them out. Okay, so that is why we don't write these ones. Now from this position, we also have 3 hydrogen atoms. Now the question is, why? Why do we have 3 hydrogens here, but we have 2 hydrogens here? And the answer is actually pretty simple, pretty clear. As you can see, we know that there is a carbon atom within that position, and every carbon atom must contain 4 carbon bonds. So this is 1 bond, this is another, and this is a third. This is going to be the 4th. So that makes for 4 bonds around these carbon atoms, which is exactly the requirement for carbon atom. If you come to this, we also got 4 bonds. So everything is actually in place, everything is in order. But as we said, these ones are the ordinary hydrogen atoms. You do not really need to write them out, except you actually need to use them. In this case, we don't need it. So I'm just going to take them out. What we need are these ones. Now, for this one, we just need one hydrogen atom. So let us bring the hydroxide ion, which is actually the base or the nucleophile, and of course that is going to be the catalyst in this case. Now you're going to have this collect one hydrogen away from here. That is the first step for aldol condensation. You always have the hydroxyl group, well, the hydroxide group rather, that will collect an alpha hydrogen and create an enolate ion. So that is going to be what will happen. And here you're going to form something like this. So I would have a negative charge there. Then we're actually going to form water, because as the hydroxide group takes out of the hydrogen, that will form water molecule. So this is what we have. Bear in mind, this is the enolate ion. Like I said, you could have this bond go over to this place and this bond detach, and that would form something like this, which we said are resonantly correct or equal with each other. Just going to take this out and write this here. So this will be the oxide, and this is going to be the double bond to this other place. And so this is what we have. This is going to be an enolate ion because we have an alkane group right here, and this is an oxide ion which could form an enolate. So this is called an enolate ion. You just need to hold that at the back. Very useful as we continue this class. This is the enolate ion. Okay. So that is what we're going to form. And like I said, this is in resonance with this other one. And this is more favorable for the continuation of this reaction. So instead of using this resonant equivalent, we're going to use this one. Now this is going to form this by this way. So there will be the collapse of that lone pair of electrons, or in this case I'm just going to call it an excess lone pair or an excess charge, and that will cause this to detach and form. So I'm just going to show it over here. So that is what is going to happen, and that will take us back to this. So that is what you need to react with the other molecule, which is this one in this case. So let us write that out. This is a hydrogen, and we have this here, and we have a negative charge here. And this is supposed to react with this molecule. So I'm going to take it here, and we're going to have something like this. And as you know, this carbon ion, which in this case is a nucleophile, would attack the carbonyl carbon. So this is going here, and this detaches, and that is going to form a new thing in it. And let us look at that. What is that going to form? So first off, we're going to write out the first structure. This is a hydrogen, which is connected to this stuff, and then you have this, right? So this part of the molecule, I'm just going to push it downward, and this is the excess electrons which you have, and this is connected to this, right? So this is what you have, and like we said, this goes here. This is the same thing as you have here, and this bond detaches. So need to wipe this out. Okay. Yep. So this is going to form something like this. You would have the hydrogen atom connected to the oxygen with the carbonyl carbon, and you have this one methyl group which is stretched or dropped down, and there is now a bond between this alpha carbon with the carbonyl carbon in this case, and you need to know that there was a hydrogen atom. So where am I going to put that? Well, I might just put it here. This is the hydrogen. And well, I think I'm going to make it disappear from there and make this to be formed first. So we have this, and this is going to be the oxide ion. So well, I might well put the hydrogen over here. So this is the hydrogen I'm talking about. Now, what is the very last step? You need the water, which actually was formed as a result of the deprotonation of the first species. So this oxide ion is going to snap out that hydrogen and cause the bond between that hydrogen and the oxygen to return and reform the hydroxide ion. And that is pretty acceptable, and really it actually needs to take place because we have already said the hydroxide ion is a catalyst, so it really needs to reform. So this is going to be the product. So you have this and you have this. Now, of course, you do not really need to write this hydrogen because, of course, it's going to be with that carbon atom. So that is going to go there. And this is what we're going to form. So this is the molecule. What is going to be the name for this molecule? So we're going to say we have let's begin counting from this place. So this is 1. Let's say this is a 2. And this is a 3. So we actually have a cyclohexyl group on position 3, and we have a methyl group on position 2. So there are 2 ways you could actually name this. You could name this using the normal form, and here we actually have a propanol, but we have an alcohol on position 3. So let us try to do that. That is going to be 3-hydroxy. This is 3-hydroxy. Okay, I need to take out the L. And we have a methyl group on position 2. So that is going to be 2-methyl. And then we have a cyclohexyl. Well, I think the cyclohexyl should come before the methyl. Now, do not really think about this cyclo prefix, but you should really consider rather the hexyl. Now, this is an H, which actually comes before the M. So we need to write the cyclohexyl first. So I'm going to take this out. And this will be 3-cyclohexyl. That is going to be 3-cyclohexyl. And then we have 2-methyl, so I think I'm going to wipe this out and write the name in a more clear form. So this is 3-cyclohexyl, and then you have a 2-methyl. And then you're going to have the propanol. So that will be the name for this compound. 3-hydroxy, 3-cyclohexyl, 2-methyl propanol. That is the name for the molecule. So this is basically how to form aldols from aldehydes. If you have 2 aldols, well, 2 aldehydes. If you have 2 aldehydes, you need to combine them. You need to combine them in the presence of a base. And that base should be the OH group. Or in this case, I would actually say the hydroxide ion. And that must form an aldol. So this is going to be the aldehyde group of the aldol. And I might just well write this as the R group, or there might be not in here. That depends actually on the length of the chain. And on this side, we're going to form the alcoholic group there with the R group. So if this is going to be the 1 and this is going to be the 2, this will be the 1 and this is going to be the 2. So basically that is how the stuff works. That is how the mechanism and the reaction works. So hopefully by now you know how to work aldol condensation.